Right.
So today's lecture will be actually 3 parts. And I will make this first part a bit shorter because I want to go through the second part, which is object-oriented programming, a bit more than I have done before. And I think Matplotlib is kind of self-explanatory when I go through the basics. And then I have added some stuff to the object-oriented part. And then finally, we'll go through CALFEM for Python as an introduction. So most of the time when you do numerical, you want to do some plotting and do diagrams and present results in a way that it's not just numbers. And with NumPy and a code installation, there is a Python module called Matplotlib, which can do this. It's very like the way you plot in MATLAB. So you will probably recognize a lot of the stuff from MATLAB. And we will be using a subset of this module called pyplot, which contains those commands that you are probably seen in MATLAB already. So just to say also that Matplotlib is just much more than just this plotting routines. There's a complete graphics library for implementing any kind of graphics that you want to visualize in Python. So there are some links here on the top where you can find some summaries on the documentation of the commands. So there's also some tutorials here. This is a very nice page where you can, they have a gallery of different plots, and you can find one plot and you find the source code how to implement that plot. So how do you use Matplotlib in your own code? So as this is a Python module, we need to import it. This first code here is just when you're running inside a notebook that we want the plots to appear in line of the code blocks. When you're running a standalone program, which your program will be at the end, you don't need this, and we will use some other commands as well. So let's import this. And the user convention is that you do matplotlib.pyplot as plt. So all the commands that we will use will have the prefix ELT. And you'll probably see a lot of code with that prefix as well. So very simple plotting. Pyplot or Matplotlib doesn't really need NumPy to plot, just things that are in what's called iterable in lists-like structures. So the one simple plot here is to just put a list of numbers here, and then you do plot. And it's also important when you're running it standalone, like your program later on, you need to call this plot show command. It's not strictly necessary when you're running in a notebook. It doesn't hurt, but if you don't put that when you run standalone in Visual Studio Code, for example, the plot will not come up. And you can plot multiple plots, but you only have a single show command. You don't have to have a show for each plot. You can do all the plots and do show later on. Then the program will stop in that command and wait until you have closed all the windows. So you can see you have plotted 4 numbers, value 1, 5, 3, and 4. So it will auto scale the access to the data. So in this case, we didn't have any x-axis, only y values. If you want to plot NumPy arrays, that is also perfectly doable. In this case, we need to have a similar command in MATLAB where you define an x range. So in MATLAB, you can do 0, colon, and then the step length, and then the end value. And you can do this in NumPy as well. And you can use the command called mp linspace here. That will take the start value here, the end value, and how many values you want in that range. So it will interpolate between those two and provide you with an x range from 0 to 2 pi and 50 values. Then you can use, to create the y range, you can do mp.syn or any function in the np NumPy toolkit to produce the y range. So it takes the x range, computes a corresponding list here with y values. It looks something like this. So you can see here that I have 0 to 50 values here going from 0 to 2 pi, which seems to be correct. So this value is also included in the linspace here. So you get the loss value included here. And now here the y values are completed automatically. So now we can plot those values. We can do plot x comma y, and now we get a nice sine function here. So the default is x range. So all other parameters are optional. So you can plot with just x values, but you can also plot with y values here. And then you get this output. Just like with MATLAB, you can change the appearance of the plot using the third parameter here, just a string here. So this says that I want to have a red plot with O rings around it. So this will plot X and Y with circles that are red. I hope. Yes. Then if you add a dash to the string here, you will have blue here for B and O for circles, and I want to also have a line between them. You can have just a dashed line. Then you have double dash here, and then the color is the first option here. Like this, and have a dash line. You can have with blue with a processor here as well. Green process with the line, like this. So there's multiple ways of combining these together. I will skip this assignment here. You can do this on your own, or I can run it here. So I have a function here I want to plot, and use a blue line. So the first thing I do is I create the X range here from 0 to 2 pi. And this time I increase the resolution here to 200 points. I computer the expression just like I would like normal math expression, just make sure that we have the .rp here as a prefix. Otherwise, the math scene function doesn't take an arrays input. So this is how it can look. You can also plot multiple series in the same plot. So then you create two series here, x, y1, y2, with two functions here. And then you can add them together here. So x, y1. And then you have the parameters for the first series, x, y2, parameters for the second series. And then you plot them. So here you can combine two functions in the same plot as well. You can also change the properties of the plots in other ways. So for example, if I want to change the line thickness here, I can add this option here to the plot command, line width equals 4. That will change the line thickness. And you have to look at the documentation for Matplotlib to get all these. There are a lot of these attributes that you can add to the plot command to change the appearance. There's also, so now this changed for both the series. If I want to change this only for one series, or have different options for the, you can actually, on the left side here, you can assign line 1 and line 2. And the line 1 will be the first object here, which is the, let's see here, the red one. And line 2 will be the blue one. These are objects that you can set the attributes on. And then you can see here that there is options here for setting the values independently. Set line width 8. So there we have line 1 will have 4 pixels wide, and the second one with 8 pixels wide. So I can do different thicknesses. You can also, if you just have one parameter here, you can get the object with all the, basically a tuple with the different axes in it. Then you can use plot set property on this here, and then you can set the properties for all the series in the plot as well. Just like MATLAB, you can plot multiple figures in Windows as well. So by using the figure command, plot figure 1, plot figure 2, you can identify your plot. So if I do this, all the plot commands following figure 1 will go into the figure with the number 1. And then if you plot figure 2, all the other commands will come into a separate figure number 2. It's difficult to see here, but this is the first one and this is the second. So it's 2 plots here. It's not one single image. There is a spacing in between. And if you run this standalone, you will get 2 windows, one for each plot. It's also possible to put plots in the same diagram as well. Then you use a command called subplot here, which is really strange here specifying this, but you can look at the plot as a grid. So the first parameter here is I want to have 2 rows and 1 column, and this is the first plot. Then I have the same 2 rows with 1 column. This is the second plot. So this is 2, 1, 1, 2, 1, 2. You can of course have 1, 2, 1, 1, 2, 2 as well to give them in a different order. So this is a single plot, 2 rows, first row, second row, and 1 column. And of course, you can do the opposite here. You can go the other way around. And then you have 2 columns, 1 row. And you can have, of course, you can have 4 by 4, 2 by 2, 3 by 3 as well. Also, you need to be able to set some properties on the labels on the axis to really plot, give a nice and understandable diagram. There is an X label command here that you can set an X name, the name of X axis, the same thing with the Y axis. See here. So now we have X value. You can see here that you share the X label here, and it only puts it once here. And then we have Y2 and Y1 here. It's also possible to add text in the diagram. So if you want to illustrate something in the diagram, you can do that using the text command. And here you have text here, and here you specify the position of the text in diagram coordinates. So it's not pixel coordinates, it's actually the value. So here I have x is n pi divided by 2, and I want the height y was 0.8. And here I can actually provide a function that are in LaTeX syntax. So in this case here, this is LaTeX code. So it will render this in math notation and put it inside a diagram. You can also tell it that it should center it around this position as well. Okay. So here you see I put the text here, so a bit below the top point here, and you can see here that you can put real formulas in here with using this LaTeX notation here. And math notation starts with a $sign and ends with a $sign. So of course you can put any text here as well, but it's a nice way of enabling you to put text in diagrams. You can also use the annotate function to create an arrow that points to something in the plot. So in this case here, I have the same the text here, XY position. I can put the XY text here, and then we create an arrow from the first point to the text position. I can give a color here, the text for black. You can see here that it puts the text here, and the arrow points to this position here, which is n5 divided by 2, which should be here, and y value 1. You can also change the axis limits, how in which range the axis should be in. Here you can see I have changes from going from 0 to pi and y from 0 to 1. I keep the things here, the notation here, and I plot it normal here again. No. So now you can see it axis goes from 0 to pi and from y-axis from 0 to 1. You can also change the scales here using the y-scale command. So you can see here you get a low scale here. And you can do this in both directions, X scale and Y scale as well. And just shortly go through some of the plots that are available. So you can do histograms. And here you have a create a random distribution here. And here you can see I want a certain number of bins. And then C1, you can get something like this. So change it to 20. You can do bar charts. You just provide an X, Y, and it will put the bar chart like this. You can do scatter plots for plotting points. And here you have one X and Y position here. And then I have scale. And then you can put colors here as well. You can do it in transparent as well. It looks something like this. You can do contour plots as well, where you have you plot things, create a grid of values here. So X and Y are grid values. And then you can use create a C coordinate by calculating an expression here over this grid. So if we run this just to show you what those X and Y means. So X is just basically the X for X value in a grid of 100 by 100. Y is the Y values of the grid of 100 by 100. And then you can use an expression to calculate the C values in each position, which is the last one here. And then you can give those parameters to a contour plot here. And you can have two different contour plots. That's one that is filled and one that is with lines. And then it looks something like this. As I did before, you can also plot images. So in this case here, I download an image here from somewhere. I get a file name here, and I can read this file into an image. And then you can do imshow to plot the image here. You can see it has axes here as well. And that corresponds to the number of pixels 0 to X direction and Y direction. And then you can also, there are some options here for how to handle pixel data. If you want to interpolate the data of the pixels here, there are different methods of doing here. You can select them and add them to yours when it displays the images. Streamlines are similar. You can do these kind of plots. You can plot in 3D as well. So the same function I did before, you can show in 3D like that. So that was a bit rushed Matplotlib. I want to show you also that you can do the first ones here. Here are a lot of information about Matplotlib. And a really nice part is, I think they have the examples here. So if you're looking for a certain plot that you want to do, you can browse this gallery here, and then you can look at, for example, I want to look at this one here. Then you get the code, how to achieve that plot. That's really useful. Instead of just experimenting around with all the different options here, you can take an example here and modify it yourself and run it. So it's really a good idea to look at this. You can see there is a lot of plots. Anything that you want, you can find here. So before you start experimenting with the commands, look at the Matplot gallery and see if you can find the right plot. So now to the second part. Object-oriented programming. So this is something that you already now, when you have started using Python, are using already without thinking about it. So the idea with object-oriented programming is that you combine data and method into a single entity. So an example, this could be the string that you have seen in some of my examples, where the string has a method called split. So the string knows how to divide itself into smaller strings. That method is combined of the string object, so it knows how it can split itself. And objects in programming context is often described with nouns such as point, circle, equation, model, square, array, string, things that are nouns. And you interact with the object by sending them messages or calling methods on them to do things. And the messages or the methods are the verbs, what they can do. So a string can split. It can also do join and other commands, method that is with the object. Same thing, there is in the matrix objects in NumPy, there is a transpose method to give you the transpose. So the methods define what an object can do. In addition to the objects or the methods, there are also object attributes. So for example, a point has a position, X and Y coordinates. Those are the object attributes. You can also have attributes that connect to other objects. So you have an attribute that has, so for example, a beam in structural mechanics has two nodes that it connects to, and those nodes can be properties of the beam object. And in Python, in other languages, objects are defined in classes. So the class is the blueprint for the object. It describes how an object should be, which method it should contain, which attribute it should have, and then you can create multiple objects of that type. So you can think about object-oriented programming. You can create your own Python data types and data structures. So the list in Python is an object. It has the methods append, clear, copy, the things that objects can do itself. So it knows how to handle itself. So to compare with a different programming model. So up until now, you have learned how to use functions in Python. And you can implement most of the things using functions as well. So in this example here, I have several functions here for defining the object orientation. Or the object here, so I have a create point. And this function, what it does is returns you a list of X and Y coordinates. So in this case, we consider this as the objects we are manipulating. And we also have a function called move point. And the first parameter is what the objects that you want to manipulate. So in this case, I want to move this point, delta X and delta Y, and then take the point here, and I add this movement to this point. I have a function here called 0 point that will zero this point. I have a function called set point, that will set the position of a point, and then you have a print point. So in this case here, the functions define what you operate on the object here itself. So you hide the actual object manipulations using functions here. And you use this by, first I create a point. And if I pass the point to print here, it to print out the position of the point. I can move the point. I can set the point to new coordinate and print the point again. So here I have a data structure point that I pass along functions that manipulate that data structure. So in this example, data and functions are separated. So you have a point data structure, which is a list, and you have a function that can manipulate that data structure. In object-oriented programming, you combine these together to single objects that combine both the data structure and the method associated with that object. So we'll start with a simple. We'll define a point object. So objects are defined using classes here. So now we create a blueprint for our point. So this is our class. It should be named point. And we need something, when you create an object, you need to kind of initialize it by default. So and that is done using the def_init method here, function. So this is a special name that is defined in Python that is called when you create a new point. The first thing what's happening when you create a new point is this method is called, and then we set x and y to 0. So all points by default are positioned at x, y, 0. So now I have run this. Now nothing happened here. The only thing that happens now was I defined a class called point. If I want to use that, I can do that. And that is approximately the same when you create MP, for example, array. This is what we do here. So in this case, I want to create a P, and P should be of type point. And what happens now is that it calls the init method, and it adds x and y attributes to this object. So if you look at this here, self here, that is the actual created object. But when you do this, memory is allocated to this object. Self here is the actual object itself, and you do self.x here. So basically, this is the self. So you can imagine if you function here, this will move into this part here, that here. So P here will go into here. P is self. So here you can see this is a visible P here, P, Y. So P will be assigned X and Y attributes. Then you can create another object, Q, of the same type. Same thing. Q goes in here. It will be assigned an X and Y attribute as well. We can actually just show that this actually is all. So if I redefine this, and if I do this here, you can see here that init was called twice. So this means that if this is called when you create a new object, init, and then this is a new object, init again. X, Y are independent. So both P and Q has an X and Y attribute. So they're independent from each other. But I will remove this here now, otherwise I get print all the time today. And I can show you that they're independent here, but it's difficult to show because they're the same now. You can see here that I have print X, so I have an attribute X here. If this wouldn't be here, this object would fail and say that there is no attribute X here. But because this init method added X attributes and Y attributes, then you can see they are both 0 here because they're newly created objects. I can change P here to be 1, 2. And then you can see here that X and Y attributes of P are different from the Q. So there's another thing that you strive to in object-oriented is to hide the actual implementation of the object from the user of the object. So you don't actually want the user to be able to access the internal variables of the object. And you can solve it by adding two underscores from in front of the X. That means that you can't access this variable directly. You hide it. So now I add also arguments to our initializer here, X and Y. So I pass the position of a new point to the initializer. So this is what my position of a point should be 1, 2. So now I'm very happy now. So now I just want to print my coordinates here. And that doesn't work anymore. So X and Y are not attributes of the objects anymore because I hid them using the double underscores. And we need to figure out a way how to access the internal attributes. And also, so they're actually now called underscore underscore X. But the thing is that you can't actually use access that one either, because that is hidden from the user of the object. So how do we solve this? So what you can do is you can create methods for accessing these attributes. And that is what you do in most other object-oriented language. You have one method for setting the value and one method for getting the value. So here we add set X, set Y methods here, where we assign the internal variable. And the cool thing with this is that without changing the way you use the object, these attributes could be located in your database. They could be located on the internet. But you don't have to know. You can use the object just like we did before. Just internal mechanisms are hidden from the user, so you can implement it in different ways. So now you can do like this. You can set the coordinates here. You can do it individually here as well. Modify them. And we can also add methods for returning the value here. So I would actually change this here because going to be a bit more consistent on info, so I'm changing it like this. So I have a function called X and Y, which changes the value of the object. So you give it the value, and then I change the internal value to X here as well. Then I can do like this. And then we need a way of getting the value out as well. And then you have a corresponding function which just returns the internal attribute. So I will do like this. On-the-fly coding is always risky. So I have X, Y, X and Y. So the first one here, that returns the internal value, this sets the value, and this returns, this sets the value. So then you have X to set the value, and you have a function for setting it, and also one for retrieving it. I've got to get confused here. It's not fine. Okay, we do it like this. That will work, but it's not okay. Like that. So I have one called setX, which just sets the value, and then I have EX to return the value. You can make it even more easy to use. As I said before, I showed an example where you just do p.x equal to something. And you can make that also secure so that you don't manipulate internal variables by using something called properties. And properties is a way of creating virtual variables that you can use as just like you do p.x equal to something, or you can use p.x as a variable reference. So in this example here, okay, changed too much. I will just fix it here. We shouldn't do any changes before the lecture. What you can do, you can create properties at the end here. So here I have two rows here at the end of the class definition called x equals to property. And here you give two parameters here. The first parameter is the function that retrieves the value of the property. And the second is a function that sets the value of the property. So if a user assigns this variable x here, it will call setX. If it reads this value or accesses it, it will call getX. So here you can encapsulate, make the object really easy to use. And you can go back to the first example I showed you here that you can do p.x equals 42, p.y 84, and you can use p.x, p.y here, which is much nicer syntax than having this get set things also. If I run this now, you can see here that the first item here is an assignment. So it calls set y. This should be get x. This should be set x. Get y. Set. So first it does set x. This is assignment. Set y. Assignment. You can see it calls these methods here. You have get x because it wants to return a value. Get y returns the value. So this way you can do a method that you still can control how the inner workings of the object works, but without this complicated without the complicated syntax that you need to use to get and set x. But there is even an easy way to do this. So instead of using the property lines that I showed before and creating all these functions directly, you can use a special method here for property. So if you do add property here, and then you give x here, this is a function for returning it. So by default, property is a returns the attribute. Then you can have x.setter, which is the method of setting the X attribute here. So if you just add these to your functions here, you will have properties automatically. So now this one works just like the previous example here, but you just have one declaration for each property. So now we have worked with attributes. So now we need some way of moving this point or manipulating the points. So we need to add instance methods. So we will add a move method here that will move the object. So here you give delta X and delta Y, and then you modify the internal state X and Y here with the position here. We define it here. So now what I can do, I can define two elements, P0 and P1. I can do move them using this method here, and that will update the position of the internal position. You can see because this was by default they are 0, so this will basically move it to position 10 by 20. If I call it repeatedly, it will add to the position here. You can also add, for example, one nice method is to have this copy from. So it's nothing but you give it another object here, and it will assign the internal X and Y attributes with the incoming point here. Then you can do it like this. So you can see here I have a copy from P0. So you can see here that at the end here, that position is this position here of the P0 point. And we're going to do now. Why is it 10 by 10? There must be something wrong here. I printed out wrong. Like this. Let's see here. 2 minutes more. Special instance methods. So there are also, we have seen one special instance method. It says init here. This method is called when you create a point, but there are more things you can do. For example, if you want to print a point here and just try to print it by default, you will get this kind of output that doesn't really say anything more. I have a memory location in your computer. That's kind of useless. So if you want to have a more intelligent print of my point, we can add a special method called str. So this method here is called by Python when it requires you to produce a string output. So for example, if you print an object, Python will call this method on the object so that it returns the output, it returns a string. And here we do print out point, we print out the attributes of the points here, and return that as a string out here. So we don't print it, we just return a string out. So let's see what happens. Now it should use a little bit better output here. So in this case here, we have 0.42.084. So that is the internal state of the object. And that is much nicer output than having this kind of memory allocation instead. So let's have a 15 minutes break. And continue. Okay, I will do a quick recap. So you can use the clauses you define, just like any data type in Python. You can add them to lists like this. You can add them to points or to lists like this with a single line. And you can loop and iterate and call the print statement all of them. And as you see here, you can also, it works that's any variable reference in Python that they point to memory locations in memory. Also, what you can do is when you have an existing clause, you can create new clauses that derive functionality from an existing one. So, for example, if I want to create a circle, I can derive from a point and inherit all the nice things I have in point. For example, the position things. What I have to do then is I have to use the init function here. This is the new one for my circle. And what differs from the circle is that I also have a radius here. So what I do first, before I do anything else in my circle init, I call super here, which is the function that returns you the inherited point object class. So in this case, it will return point. It will call init on the point, and you pass along the x and y here. You don't have to do anything with them. Those are created in the init method for the point. Then you add your own attribute r here, and then you add properties for that. You have to handle copy a bit differently, so you have to have super copy from C, and then add the R here. And we have to update the string method. But the move method, all that stuff and the position handling is all done in the point clause, so you don't have to do it again. So here you can see I create a point and a circle. I have a property on the circle called R, and I can move the circle and move the point. That move method is implemented in the point clause. So circle inherits and has that functionality as well. So you can see here that works perfectly. It also adds this printing out here for printing out the radius. Inheritance is one way of expanding clauses. Another common way is using composite clauses. And composite clauses is a clause that owns other objects. So, for example, if you have a line has 2 points that you want to attach to this that is owned by the line. In this case, I have self P0. I create them internally here in the init section. I have properties P0 and P1. This one just returns the values. There is no setters here. And I have a different print statement here as well. And actually, this is kind of inheritance. Today in modern programming, they kind of want to limit. You want to limit the inheritance depth. And actually, most of the times, composite clauses are the way to go. So, for example, if you have a beam in structural mechanics, it has 2 points. It's a natural way of it owns 2 points. It doesn't have to inherit the functionality of the point because it's not a point. And here you can see here, I can create a line like this. You have line p0.x. So here you have the point. It has the x property, and I can assign them directly like this. But there is a problem with this. Or a feature. So you can see if I do line.p0 equals to point, you get this, I can't set the attributes. And this can be a feature, it can also be a problem. So what you can do, you can see here that I only provide the properties for reading here. So I only return, there's no set properties here. That's why I can't assign new point instances to the line. And that is something you can decide yourself if that is something you want. You can change this here by adding set properties here on P1 and P2. So here I have setter here, assigns the point, and I have a setter P1 here as well. And now you can do stuff like this. So I have P3 and P4. I can assign the property of the line P0 to these points here. Because now I have a setter as well. That is perfectly okay. But it's a design choice. You can do either way. So if you want to have control over the internal points, only give it a read. Don't give it a separate. But if you want the user to be able to change the points, the point instances, you can add a separate to your class. And then you can add a method here for adding the length to the line here as well. And then the final concept in object orientation is something called polymorphism. And regardless of, so in this case here, I want to explain it with an example here. I have a shapes list here. I add a point, I add a circle, I add a line, and I add a number here, integer, and a string. And polymorphism means that the correct method is always called on the method regardless of what type it is. So you can kind of determine here, if you loop over the list here, the 4 shaping shapes. If I call print, as you know, print will call the underscore str method. It will figure out that point has its own str method. It will call that on the first shape. If it's a circle, we call the circle str method, and line the same thing. But what happens here? We'll see what happens. So you can see here it calls the points, str, circle, line, and you can determine that automatically, and that is what's called polymorphism. Depending on the data type, it will call the correct method. Of course, if you have a shape.move, it will call the correct move method depending on the type. That will automatically handle. But there's an insert aspect here. We call print on a 42 floating point value. So what does that actually mean? So, as I said before, everything in Python is objects. And even a floating point value is an object. So you can actually call a floating point value with a method. So in this case here, print 42.str will call a method on the 42 object, the 42 floating point. So all objects have basic methods on them. You don't have to call them if you don't want, but they are there, and you can do it. So in this case, it's also here an example here that you can do the move method here. The correct one is called, depending on the type. Let's see here. I think I will finish that. So I wanted to do a bit more graphical illustrated version of the object-oriented programming example here. So I will switch development environment now. So I will use something called a module called Pi5. This is optional. This is not included in the course. You don't have to do it, but it's Pi5 is a module that implements a special programming API called processing, which is a creative programming tool chest. It has very easy to draw things in it. So a normal application in Pi5 has a settings method that is called once, which sets the size of the window. It has a setup method which is called once, where you can initialize things, and you can there's a draw method for drawing. So just to kind of illustrate that you can go from these abstract classes that I have to something that can actually be visible on the screen. I created a class point here, same as we did before. I implemented the draw method here to draw it on screen. And the draw method implements the commands to draw it in the window. So I stroke 1, 0 here, that is the color of the lines. This is the thickness of the line. And then I create a point here at self X and self Y to draw it out. So if I run this, it draws a small point. So this is the kind of goal of this here, but I wanted to do a little bit more complex example here. So let's see here. So I wanted to implement the particle system. So what I want to do is I want to create a base class for all my movable objects. I call it a drawable base. And this class will contain position, color, and so on. So I will just do like this, copy paste here. Paste in here. So I have an init method here. I will add some additional properties here like colors, stroke alpha, and so on. I will also add two methods here. One is called onDraw, and that is so the drawable base will set the colors of the object, and it has all these basic attributes that I need to have for something that can be drawn. And I set it up here, and then I delegate the drawing to my derived classes here. So you can see I have an empty onDraw here. So drawable base is something that will not be drawn directly on the screen. It will be used as something I inherit from. And then, so the next class that will actually be able to draw something is the particle. So particle will store the position of the object. What I need for this, I would need, see here, I will need a position and also need a speed, because this will be something that will move on the screen. So I will add derive from my drawable base, so it has the ability to change line colors and so on. And then I also have our X and Y coordinates. I have a vector for the speed. And I also set the default stroke width to 2. I add a method called update, which we will call continuously here to update the position according to the speed. And then I implement the draw here. So as I said before, I have a draw already that is called by the draw method here. And this is delegated here. So the only thing I do here is I draw a point. But I really want to have more nice particles. So I want to round particle. So then I create a round particle, derive from particle. And then I will just there. So now the only thing different from the particle is that I have a radius here. So I add a radius. I instead of drawing a point, I draw an ellipse with the radius size here. To make the particle system stay in one place, I also implement a boundary. So that is the limits that determine where the different particles should bounce. In this case, I define x, y, x max, y min, and so on. And also a method to determine if the particles are inside the box. And I also have checks here to check if they should bounce and so on. So I add those to my empty class. This. And I have a box boundary. Then I need to implement my particle simulation. So let's see here. The first thing I need to do is I have to do I need to create a list of particles that I want to simulate. So I create an empty list, particles, and I create an empty. I also need to create this box object to self.boundary, call it. Box boundary. I also need to adapt the draw set here. This here, just that the ellipses should be drawn at the center and middle of the ellipse, not on the left upper side. But finally, I need to draw my particle or create my particles that I want to use in my simulation. The first thing I do is P equals to round particle. And I random 0.600. I place them randomly on the screen.
Yeah. Random.
Oh, random, yeah. Thank you. And then the next, I will need to set the random speed as well. So p dot vx equals to, so random is a function that's built into the sketch system. So it's already there. Random minus 6.0. So now I have the field properties already defined in the property of the drawable base. So I set it to random, of course. So colors are defined by from 0 to 250, red, green, and blue. Like that. And to make it really cool, I also set the fill alpha, which is make them transparent. But I don't do it all over, so 52, 55. Like that. And then I do self.particles append. So here is object orientation again. So part of the list has a method called append, which you can add stuff to. So I just add P here. So now I've created all my particles. So now we need to do the simulation. And that we do in the draw section. So draw will be continuously called. And then we give it one, it's called every 16th of a second. So 60 frames per second, this is called. And then I call the boundary to check the particle. And then I call the particle to draw. So if everything goes well, this should work. It didn't, of course. We do it like this. So I have my pre-cooked version here. It's almost the same. So let's see, if everything should work, it should look something like this. There it is. So this is so each of these here are an object that knows how to draw itself. It has all the attributes, yellow, green, red, blue, and so on. And it knows how to, it also has a X and Y speed, and you update it and remove its position over the screen. So this is a practical example of how you can use object-oriented in a simulation. And actually, this is how many of the simulations that run for molecular and particle simulations are actually implemented. You have a lot of particles that have speed and mass as well. And then you update the system and then you visualize it like this. So back to the other stuff again. So I hope you get the concept of what object orientation is. And the final part we'll go through today is the CALFEM for Python part. So this week's worksheet will be to implement a simple finite element model in one of those categories that I described. And what you need to do is implement a model class that will kind of handle the simulation of the setting up the finite element matrices and assembling into system matrix and solving the problem. So what is CALFEM for Python? So it's a subset of the routines implemented in Python. And we are almost at the point that it's not a subset anymore. It's almost a complete CALFEM for Matplotlib. It uses NumPy for matrices and arrays. We also added routines for generating meshes. So you can generate triangular meshes, quad meshes automatically in CALFEM. It uses the triangle and G-mesh mesh generation tools to produce the actual meshes. So those are external tools that are really efficient at doing meshing. It also uses Matplotlib for the plotting part. It's implemented in several modules. You have CALFEM.core, which contains all the element routines, some of the system routines, but mostly things that are not visual, so all the computational parts. There is a CALFEM.utils that contains several IO routines for reading and writing stuff to disk. Some other things that didn't fit in other modules. CALFEM.geometry contains function for defining geometry, which you will then use for the mesh generation parts. CALFEM.mesh, which is all the mesh generation routines. And then the visualization routines called CALFEM.vis and CALFEM.vismpl. So we will use the vismpl in this course. When you have installed your packages VSMN20, you don't have to do this step here. This is just to be able to get CALFEM for Python in this notebook here. So I will run this here. So this should be already in your module VSMN20. So the general procedure for FACalc, you probably have already done this in multiple courses of structural mechanics. You define the model, you generate the element matrices, you assemble the matrices into the global stiffness matrix, and you solve the system equations, and you calculate element forces. So what I'm going to show now is kind of repetition of you already done, but now in Python. So system of springs, you probably see this from the CALFEM manual. But what we do first is we import the Python modules. So we do NumPy because we need NumPy, CALFEM core as CFC, and CALFEM vis as CFB. So I use also this prefix here to make it easier to write the functions here. So you don't have to type CALFEM.core.beam2e. So like that. We define the topology matrix. Also, CALFEM uses one-base topology definition. So it's the same as the MATLAB version. We decided to do have the same, so we can have the same examples. So the degrees of freedom starts at 1. We define the topology here. We define the stiffness matrix here, and we use zeros here, 3 by 3, like this. We just define some spring properties here, and we call the spring element like this. And that will return you the spring matrix here. And then we assemble into the global stiffness matrix. So there is a command called CFC assemb, which is the same as for MATLAB. We push in the EDOF matrix. And here you have, of course, you have to use indexing with 0 because this is a NumPy array. And then we assemble it into K and the stiffness matrix KE2. So the element topology, and we use indexing here as well. So row 0, all columns, K, KE2. But the difference here is that you don't, as in MATLAB, you have a return it outside here for K and K2. We don't do that here. It's assembled in place. And as I said before, you can do this with arrays and lists that you can modify them inside a function, which we do here. So you can see here it looks like a reasonable matrix. And finally, we solve the equation system here. So we have, first we do boundary conditions, 1.3. We have the forces here. We also have to think about the indexing here is zero based. So this means that this is the second degree of freedom here that we apply. We solve it here, the same command here, A, R, which is the displacement of reactions, K, F, BC. So if you just define, by default, BCs in CALFEM or Python are assigned to 0 as the boundary condition. If you want to have values for the boundary condition, you have to have another array that we provide as an extra input here. So then you can see here the documentation here. You have a BC prescribed, which is what we have now. And we also have a BC val for the actual values that you want to assign as the boundary condition. And also the equation here. And we got the reaction force. So that should be similar to the CALFEM. And then we extract the element displacements here using the extract LDISC. And using the same method using normal CALFEM. And then we can calculate the spring forces here using the spring S command. So it's very similar. Then we have a bit more complicated example here with bars. We have 8 degrees of freedom. We have bar elements. In this case, we have 2 degrees of freedom per bar. So 1, 2, 5, 6, and 5, 6, 7, 8, and 3, 4, 5, 6. Now we have a degree stiffness matrix of 8 by 8 and a force vector of 8 by 1. We define our bar properties here and assign them to EP1, EP2, EP3. And we define our element coordinates. These can actually be lists as well. You don't have to have them as arrays. So you can have the coordinates and give them as lists as well. And then we create our element matrices. We assemble them together. And then we solve the equation system here. So how we do here, we have only 2 degrees of freedom that are movable. So here we have 1, 2, 3, 4, 7, 8 that are fixed. And then we have a load at degree of freedom number 6. You can see here that we only have displacements here in these 2. And then we have reaction force in the other ones. And we calculate element forces like this. Okay, so this is not doable if you have more elements. So we need to figure out a way of doing it this more efficiently. So we have a bigger frame here with a force here acting in 30 degrees here, and then we have all these elements here. And then we have topology. This will be more complex than before. We create our, don't forget to press that. We have the stiffness matrix here, 12 by 12, and the force vector of 12 by 1. Some element properties. We also have the EX and EY arrays here for our element coordinates. So next step, we want to make it more efficient to actually assemble the system here. So here we use our the zip function here to be able to loop over the element X coordinates, element Y coordinates, and element topology. We do that by specifying EX, EY, EDOF. That will take one row for these arrays all the time. So you can call KE equals to CUC bar to E, ELX, EY, EP. We have all this is the same for all elements, so we can just keep that one. And we call ASM element topology, which is one row of the EDOF array, K, KE. To solve the equation system here, we provide our 11, 12 here, the force. And as everything is 0 here, we can just provide the degrees of freedom that are locked. So 1, 2, and 3, 4. Now we solve the problem. So now we have the other way. Now we need to calculate the element forces the other way around. So now we do the same thing here with a loop, but now we loop over element displacement. So we have this command here to extract our element displacements using EDOF and solution vector. We create an empty n array to store our element forces in. Then we loop over all these three here, and we call bar2s here, ELX, EY, EP, and ELD. And then we store that in the n array and print it out. So now I compute. So this is a way of, so what you probably will do is use some of these, this code to implement your solver. And in the first worksheet, there will be a very simple solver with just four elements that you have to assemble together. But it's a good idea to implement this here directly in your first worksheet. You can also combine having, so this is an example of having both bars and beams in the same model. So as we have beams, we also have rotational degrees of freedom in each node. And here we then we specify, so we have 18 by 18. We have a force, and then we define our coordinates, and then we define two arrays for the rotational degrees of freedom and one array for the XY degrees of freedom for the bars. We also have one element property for the bars, this is the beams, and then one for the bars here. And here you can see that we extract, let's see if I can that. We use the coord extract command here, which is a nice command that can take this coordinate syntax, return EX1, EXY. So now we get the element coordinates X and Y from the topology and coordinates. And then we need to have two loops. We need one loop to assemble the elements, the beam elements, and one loop to assemble the bar elements. And then we have the prescription, prescribe degrees of freedoms, and then we solve the system. So that was what I want to do with CALFEM. And this is, there should be links to the CALFEM documentation on web pages. There's also on the CALFEM web pages, there are also a lot of the examples that you can run yourself. I can show you here. So if you go to this web page here, CALFEM, so CALFEM Python here. There is an examples folder here. And here you can see there is a lot of examples for how to implement different things. The normal EX things here, these are basic CALFEM things. That's probably is what you want for this worksheet that you're doing now. The EXM stands for meshing, and the EXS is for static thing. So, but there is a lot of examples here you can browse through, and there should also be should be in the Canada side as well. Let's see here. CALFEM for Python. this documentation is here as well. Here you can find all the tutorials and examples. I can link for, and there should also be a function reference here for all the commands. So everything should be in here. And as I said, for the example for this worksheet is very simple. You should implement the model that just calculates a very simple structure of 4 elements and computes the forces and displacements if you have a stress problem, or flows if you have a technical problem. So that was what I wanted to show you today.